Hello Panther and welcome to our new video. Today I will show you how to derive some formulas including complex numbers and complex integrals. Here I have some complex function fz hovering above complex plane C, and let us imagine there is some z0 function, z0 point, complex number, and there is a radius r, real radius, and there is a circle in this complex plane. Above there I will denote function g as a function of fz0 plus r times e to the power of I phi. This function is basically evaluation of these heights, complex heights, which are complex, but this is only demonstration as this function g. Clearly, we are able from the previous videos to derive an expression for a derivation of g of phi in terms of its complex its series in its Fourier series. Since the period is 2 pi, because this is circle and this is phi, so its period is 2 pi. That means that g of n is equal to this form, because the period is 2 pi. This is the basic Fourier series. Well done. Okay, but since we can write it like this, we can also write very interesting formulas for that. Let us imagine we perform a substitution. We perform this substitution. Let us imagine that z is equal to z naught plus r to the power r times e to the power I phi. This is just some complex number, and let us imagine you have this complex number defined as this. So this is basically some complex number on this circle. Well, okay, so that means that but since this holds, you are able to express e to the power of I and phi in terms of this, because since z is equal to this, so you can always write z minus z0 to the power of n is equal to r to the power of n times e to the power of I times phi. You clearly see that equation, so you can plug it in, and you will get that for this series is equal to sum from minus infinity to plus infinity times g of n divided by r to the nth power z minus z naught to the nth power. Well, this is the formula, because this is to the nth power, there should be n, so this is n. I will substitute this for that. Okay. Well, and the next thing is that you are also able to express the differential of z, which is exactly equal to differential of this is 0, this is differential, so this is very easily written as I times d over phi, but since this is our original z, so this is equal to z I times z minus z naught times what? Times d of phi. So we are able to write this as 1 over 2 pi integral, and the integral is now we will perform a substitution. What is now the integration numbers? Yes, this integration is now performed on z, which is complex, and this notion is basically how to denote curve. Yes, so this is curved, this is circle, some circle of radius r. This integration is written as this, and g of phi, it's basically f of z, because I've denoted this as f of z. You can clearly see this is going to be e to the I, and phi is basically this over r times n, which means to the minus power is this minus times r to the plus power, so this is basically r to the n times this to the minus power, but there is another minus power from this. I will substitute d phi for this and dz, so this will give me fz divided by z minus z0, and there is to the nth plus first power times dz, and there is I divided by this. Okay, well, and if you denote Cn as Gn over R to the nth power, you will get that f of z is equal to, and this is equal to this formula, well, and this formula is equal to this g of phi, and if I substitute this as c of n, so this is sum from n minus infinity to plus infinity times c of n times z minus z0 to the power of n, where c to the cn is given by this formula divided by r to the nth power, so this is cn is 1 over 2 pi I, complex integral where z is exactly r times f z divided by z minus z0 n plus the first power dz. What is interesting in here is that r could be any number, so then you are able to express any z in complex plane, because any z is reachable from any other z not point, yes, for given r and theta. Okay, so this is very interesting. So this series, which consists of also positive and negative powers, is called Laurent series. Laurent series, and these are coefficients of Laurent series given by this particle formula. Okay, well, next, what is also known is that whenever this function g of phi has a Taylor expansion, what does it mean? Or function fz, which is equivalent here, that means are you able to express this as a Taylor series? Taylor series is given as this function. This Taylor series is from 0 to infinity instead, and there are some coefficients. I will denote them again with Cn, and this is z minus z0 to the power of n. For Taylor series, which looks like this, negative coefficients are 0, clearly from this. And when function z has a Taylor series, it's called, I think, holomorphic, but I'm not sure. Holomorphic, and that means there are no singularities. There are no singularities because there is these are polynomials, and limit of polynomials for sufficient low value of z is a polynomial, so there are no singularities. There can be singularity far away, but there is no singularity in local space of z naught. If there is a singularity, then there would have been some non-zero Cn term for negative n. Well, okay. What next? What is next interesting thing is that you can also write a Taylor series as this, as a sum of n from 0 to infinity, n of 0 to infinity. And what are the coefficients of Taylor series? Well, you are able to write that as nth derivative at 0th term divided by n factorial times z minus z0. Okay, to the nth power. So for f, which are expressible as a Taylor series, you have a correspondence. That c of n, which is f derivative times z, so I will write it as this, nth derivative at z0 is given by n factorial divided by this. I will write just this, n factorial, substitute this in the cn, and cn is given by this, so n factorial divided by 2 pi I times integral of z is equal to r fz divided by z minus z0 to the n plus first power dz. This formula is very neat, and I hope you will remember it later, because you will use it for computation some series. Now I will show you what residue is and how to compute integrals of a form. We are just not using Cauchy's theorem. We are just using this Taylor series approach to complex functions. So a road to residue theorem, which says how to compute some integrals. Let us imagine that there is some function h of z which looks like this, which looks like h minus m divided by z minus z0 to the nth power plus dot 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 h minus 1 divided by z minus z0 to the first power, yes, plus h0 plus h1 z minus z0 and so on. This function clearly has no Taylor expansion. Why? Since there is a pole of order m. You are here dividing this equation of pole of this factor z minus z0 to the nth power. So at z is equal to z0, there is no Taylor expansion. Well, interestingly, you are still able to find a formula for an integral which looks like this: integral of h of z dz at z is equal to r. Our goal is to find formula for this integral. You know that this I will compute. This I will compute, but you know clearly from this function g of n what this value of integral really is, because whenever you are integrating this formula, that means you are integrating this, and so here n is equal to -1. So the result is 2 pi I. Whenever the function can be anything, so when the function f is h of z, this type function, then clearly this holds anyways. So that means that f of z, integral of f of z, just f of z when n is equal to -1, is 2 pi I times c minus 1, where c minus 1 is this expansion, is in this expansion. So this integral is 2 pi I times g of -1, where g of -1 is called the residue of function h of z at z is equal to z0. Well, our goal is to find a value for h of -1 from this series. Clearly, this function does not have Taylor series, but this has. I will multiply this function by this pole, and I know the order of pole is m, so that means that hz times z minus z0 to the nth power is equal to z minus 1, z minus m plus dot dot dot, and there is h minus 1 times z minus z0 to the power of m minus 1, and there are the other powers as well. Well, clearly now I will try to find this function. I will call my new f0 function, and clearly I am able to write it. I will define this function as my fz function, and derivative the z with respect to this derivative of fz, m minus first derivative, m minus of this, at z is equal to z0, is equal to m minus 1 factorial, and the only term which survives is this, m minus 1 factorial times h minus 1. This is just derivative. I will perform a derivative on this, and this will be put here in derivation, and you will get h minus 1. Well, so from this you will get that h minus 1 is equal to f minus 1 z0 divided by m minus 1 factorial. Well, but there is another expression. So yes, you are able to find this, and so that means that is equal to this 2 pi I times h minus 1, which is 2 pi I divided by m minus 1 factorial times this derivative, so that's dz m minus 1th derivative of this function, which is hz times z to the m minus 1 power evaluated at z is equal to z0. And this is very interesting formula called the residue theorem, where this part is the residue. Oh, is the residue. Yes, this part with the factorial, this is called the residue of hz z0. Well, I hope you enjoyed this short video, and maybe next time